Hello and welcome to Mark's Tech Talk. In this edition, we're going to be looking at fiber optic cable, particularly as it's applied to communications cables. This is a cross-section of a fiber optic cable, and in the center you'll see the core surrounded by the cladding. That's the actual active part of the fiber that actually propagates the light. And this could be glass or it could be plastic. The early fiber optic cables were almost all glass, and today most of them are almost all plastic. Surrounding that core and cladding is a buffer layer. You can think of that as kind of like a pillow to protect it from damage. And then there's a strength member there to literally add strength to the cable. And then a jacket material which protects it from the elements and so forth. So how does this work? Well, here is a illustration of the core, and around that we have the cladding, and the cladding is a slightly different material. If you think of it as glass, the center part of the fiber, and we're looking at it from the side, would be the part that conducts the light, that propagates the light. And the cladding is another material of the same type that would keep the light contained within it. So the red arrow would correspond to the light. You can create that light with either an LED or more likely for long distance communication, you'd actually use a laser beam. Now the concern is what happens when the light strikes the side wall, if you will, of the cable. And what we want it to do is to reflect. And we can get it to reflect by virtue of something called total internal reflection. Total internal reflection. And you may have encountered this in a swimming pool. And essentially what happens is if your light enters the cable nearly parallel to the cable, all of the light is going to get reflected off that surface between the core and the cladding. And that depends upon this physics idea of total internal reflection and something called the critical angle. N2 here is the index of refraction of the core material. N1 is the index of refraction of the cladding. And the arc sine of N1 over N2 will tell you what the critical angle is. And the critical angle is measured to the perpendicular. If that angle is great enough, in other words, if the light is nearly parallel to that surface, then all of the light will be reflected back down. Again, think of the surface of water and air, and sometimes you cannot see in the water or out of the water because that surface, the light actually gets reflected across that surface. So the same type of thing is happening here. Total internal reflection, because of the difference in the index of refraction, if the light is nearly parallel, then the surface there reflects the light back in. So that contains the light within the fiber. So what we have is the light basically bouncing back and forth along the length of the fiber. And it continues doing that until it reaches the other end. And that's how we propagate light down the fiber. Now, if we modulate that light, we can actually include information there. Now, there are several different types of fiber optic cable. Let's look at the easiest conceptually, and that is the step index. That is where we have the core material being one index of refraction, and the cladding material being another index, and we get that total internal reflection at that surface. The problem with that is if you have light that hits it at different places, you can actually wind up with several different paths for the light to take. And when you have several paths like that, at the end of your fiber, they're going to combine and give you the total amount of light, but they may not be totally in phase. And if they're not totally in phase, you're going to get destructive interference. In other words, you're not going to get very much light out because they're each of the beams are canceling with one another because they're not in phase. So that's one of the downsides to step index fiber optic cable. And you can see each beam taking a slightly different path and therefore taking a slightly different amount of time, or length if you will, and therefore getting that phase difference. So these multiple paths result in destructive interference. Okay, in the terminology that is used for communications, this is called dispersion, and this leads to not very much light reaching the other end because again it cancels out. So this type of fiber is not really good for long distance communication because of this problem. Here's another type of fiber optic cable. This is referred to as a graded index fiber optic cable. And here we don't have simply two materials. We have the core and then we have the cladding, but then there's not a sharp transition between those two. There's a gradual transition. So it changes gradually from one index of refraction to another index of refraction. And again, if it's glass or plastic, that might be because there's some mixing occurring when they manufacture it. They allow this to mix, and there's no longer a sharp transition between one index of refraction and another index of refraction. So what happens with this gradual change is that the light bends rather than reflects. So if a light approaches the side of the fiber, it starts to bend rather than being a sharp reflection, and bends back down and does the same thing again. And every time it approaches the side, it bends rather than a sharp reflection. This is called a graded index. And you got a slightly better result here, a little bit less dispersion with this. But this is the type of fiber that we use most of the time for long distance communication, and this is called single mode fiber. And with single mode fiber, essentially we use a core that is very, very thin, and therefore there's only one light path for the light to take. It really doesn't allow for that reflection back and forth across the width of the core, and rather simple one path, and therefore there's less destructive interference because there is only one light beam and one path for the light to follow. This time, the only time a reflection would occur is if the fiber itself is bent. If it's not in a straight line, then you're going to get some reflection. But again, very little, because the core is so narrow, you really only have one possible path for the light to follow. So the type of fibers we have the step index and the graded index. Both of those are multi-mode, which means there's multiple paths for the light to travel. And then the single mode, which is the very, very thin one, where there is only one way for the light to travel down. And the single mode, again, is the one we use mostly for long distance communication. So step index has high dispersion. That's the canceling out of the light beam. These are used for medical imaging, and basically in this application you're only looking at a very, very short piece of fiber, perhaps only 3 feet or something like that. It really is not much of an issue there because the length is so short. A little bit less dispersion in a graded index, and you may see these in local area networks or something like that. This is again is a multi-mode, but because it's relatively short distances we're talking about, it is not a huge issue. Here is a single mode, and again this is for all long distance communication, for telephone communications, cable TV, the internet, things like that, where you're sending information a very long distance. You use a very, very narrow core and only one path for the light to travel, and therefore there's very little dispersion in the cable. So here is a fiber. This illustrates the size that we're talking about here. I have laid a fiber across a dime, and what you're seeing there is actually the fiber surrounded by that protective buffer coating, And the actual fiber is, you can see on the left-hand side, I have a little arrow pointing to the actual fiber. It's extremely small. Typically, it is smaller than human hair. Very, very small and very difficult to see. So again, for scale-wise, that's on top of a dime. All right, this is an actual fiber optic cable. You can see it is color-coded because there's actually several fibers here. And each one is a different color, so at the other end they know which fiber is which. And on each fiber you can send several different beams of light, each one a different color, and then you can use a filter, a prism or something like that, to separate the beams out at the other end. And you can actually get multiple communications channels on each fiber, and each communication channel is capable of handling large amounts of data. So this has pretty much replaced copper wire for all kinds of long-distance communication. Here's an example of some fibers in a server room. You can see where they have actually added some connectors here to facilitate the fiber connection to the equipment. And they come in pairs because usually they, for these applications, they'll send the information one way on the fiber. So you have one fiber going one way and a different fiber going a different way. One thing you have to be concerned with fiber is something called the bend radius. And what this means is that when you are installing the fiber, you've got to be careful that you don't bend it too sharply. Because if you do that, the light will no longer have that angle so that you have total internal reflection, and therefore the light will escape through the cladding, and you'll lose that light. So you got to really be careful of that bend radius to maintain that total internal reflection. Other issue here, if you bend it too sharply, you can cause micro cracks, and these micro cracks, of course, will interfere with the propagation of light. So you got to watch for what's called bend loss, and therefore the attenuation of the light, because it is not being reflected properly. You don't have that total internal reflection. So here is an illustration of that. You have the fiber is a little bit too sharp here, and you see some of the light kind of escapes out the side, and I don't have a real good illustration here, but right in here, if you bend this, you can kind of break the fiber, but even if you didn't break it, some of the light would escape out of the fiber and only some would continue down. So that's what you want to avoid. You want to avoid that by bending your cable too sharply. That's a no-no with fiber optics. You have to be careful of that, particularly during installation. Okay, so you can see I kind of had my animation out of order, but right at the edge of that fiber, some of the light is escaping out there. Okay, so typically you'll say bend radius should be about 10 times the diameter of the cable. With a no-pull load, if it's under load, it should be about 15 times the diameter of the cable. And if you have multiple fibers in the cable, you can then handle it slightly differently there. So there's guidelines from the manufacturer as to what the bend radius should be. So you got to be careful of that with installation. Okay. All right, so that is just a little introduction to fiber optic cable. That's it for this edition of Mark's Tech Talk. Hopefully you enjoyed, and tune in for more.